where each of the red hydrogens are pointing either up or down, what happens is through a process called ring flipping, these red hydrogens pointing either up or down then become, on chair number 2 over here, the hydrogens that are painted in blue. They kind of switch to the position of an kind of an equatorial plane of the cyclohexane molecule. This process of ring flipping is achieved because these hydrogens obviously want to repel each other as much as possible, and since they can't freely rotate, instead of doing so, they are in this constant alternating form of the cyclohexane chair. And these alternating forms are arrived at through a process of intermediate changes in the cyclohexane molecule. All molecules seek the lowest energy configuration that they can possibly achieve. And these intermediate forms of the cyclohexane molecule that cause this ring flipping process to happen are much higher energy than these default standard chair configurations of the cyclohexane molecule. So we don't call these intermediates, these intermediate configurations that cyclohexane takes, as actual configurations. We look at them kind of more as transitional arrangements in 3D space that they take in order to flip to their alternate chair form. Now there are many names for these intermediates. They take on the name of half chair, boat configuration, inverted boat configuration, but all you really need to know is that if we start with chair number 1 over here and chair number 2 over here, the intermediates that arise out of this ring flipping process are always going to be much higher in energy. We see this intermediate here. Now the potential energy of this intermediate of the cyclohexane ring flip is about 10.8 kilocalories per mole higher in potential energy than its original chair form. This second intermediate is a little bit less higher in potential energy than the default cyclohexane chair, but then it goes back to an inverted intermediate, which is still 10.8 kilocalories per mole higher in potential energy, and then it finally descends back to the inverted form of the second chair. And I want to actually show you the process of this happening, of cyclohexane flipping from one chair form to its other equally stable but opposite chair configuration. Before I do show you the ring flip animation, since cyclohexane is such a complicated molecule, we do need a way of kind of accounting for each hydrogen on this molecule at any given point in time. And the way we do that is by imagining a plane in the middle of this cyclohexane molecule so that we can account for any of the 12 hydrogens on this molecule throughout the process of the ring flip. So if we can imagine drawing on each of these carbons kind of little green circles so that we can then kind of connect 4 points on this molecule in this manner. Now we kind of have a rubric or a template or a position of reference, if you will, so that every hydrogen can kind of be compared to this point of reference. And so we use this plane in the middle of this molecule to define each one of these hydrogens on that molecule by calling them either axial or equatorial. And so first I'm going to explain the equatorial hydrogens. Basically, looking at this plane inside this molecule, we can identify hydrogens based off whether they're shooting kind of straight up or straight down away from this plane, or we can identify them based on whether they are kind of jutting upwards in a slant like these blue hydrogens are, or downwards in a slant like these other blue hydrogens are. So basically, when I say an equatorial hydrogen on the cyclohexane molecule, what I mean is any of these color-coded blue hydrogens that are either kind of going at a slant down away from the plane or kind of jutting up at the same amount of slant, just in the opposite direction, upwards. And so these hydrogens on the cyclohexane molecule, we denote them as equatorial hydrogens, and depending on whether they're going down away from the plane or up away from the plane, we will refer to them as equatorial up or down. So in this case, since this hydrogen is jutting upwards out of this plane, we call this an equatorial up hydrogen. And this hydrogen here would be an equatorial down. Now, for the red color-coded hydrogens, we refer to those as axial. We refer to this red hydrogen as an axial hydrogen. We refer to this one as well as an axial hydrogen. But depending on whether or not they're pointing up or down, we refer to these from here on out as axial up, or I'm sorry, in this case axial down or axial up. So now we have some way to identify each hydrogen on this cyclohexane molecule in a way that we can account for them during the ring flip with a good degree of accuracy. And this is the convention in organic chemistry. I'm not just giving you my formula for memorizing these things. This is how we actually refer to them in the nomenclature of organic chemistry. So we can use that template to draw the cyclohexane molecule as well. So we can draw the basic form of the cyclohexane molecule, and we can start with the axial up hydrogens going first up, then down, then up, then down, then up, then down, and then we can draw the equatorial going first down, then up, then down, then up, then down, then up. And that's how we draw cyclohexane molecules. I'll kind of spread that out for you. I mean, you know, it's not the best artwork, but you understand. So now we're looking at a cyclohexane chair with the blue hydrogens in the axial position. I'm going to hit pause on the animations, and we're going to try to follow the intermediates from chair to chair. I hit pause, and now we're seeing the blue hydrogen starting to change. We get the half chair configuration, now the twist boat, the boat, to the other twist boat, and now to the other half chair, and now we're going to see that the blue hydrogens have moved to the equatorial position, and that is the process of the ring flip. The blue hydrogens have moved from axial to equatorial. Once again, we started with the blue hydrogens, in which are shown here, and the process of the ring flip caused us to go to this position where the blue hydrogens are now in the axial positions. Watch it again and see if you can see it for yourself.